Hey there, welcome to another edition of Mr. Weis Solves a Old AP Problem. And this time, we're going back all the way to 2004, number 5, for an oldie but goodie. Pretty easy problem actually. Part A starts out really nice. We're beginning by, we're working with a function. We know the derivative of this function is x squared natural log of x. We know that the value of this function at e is 2. We don't know what the function is, we only know its derivative. We do know that the function though is defined for all x greater than 0. These are all given facts to us. Part A says, find the equation of the tangent line 2f of x at e comma 2. E comma 2 being a point we already know is on the curve, so pretty straightforward. This couldn't get easier. I want the equation of a line, I need to know the slope of the line, and I need to know what point the line goes through. The point is already given to me, so all that's left is to figure out what the slope is. But the slope is just f prime of e, which is, since we know the equation of this of f prime of x, it's just e squared times the natural log of e. And you all should know that the natural log of e is 1, so this is just e squared. Thus, the equation of my tangent line is y minus 2 equals e squared times x minus e. And I would leave my answer just like that. Here we are on part B of this pretty old 2007 number 4 AP Calculus BC problem. We're dealing with this function, which we don't actually know what the function is. We know that its derivative is x squared natural log of x. We know that when you plug in e, you get 2, and we know it's defined for x greater than 0. This question asks, is the function f, which we don't know, concave up or down on the interval from 1 to 3? Very straightforward problem if you understand that the second derivative's job is to tell you about the concavity of the original function. It does its job using a plus or minus sign. If f double prime is positive, the original function is concave up. If f double prime is negative, it's concave down. So therefore, we just need to look at f double prime. So this problem seems to be about, can you take a derivative using a product rule, and do you know the derivative of the natural log, because that's going to be involved. So we have a product rule. The derivative of the first term is x squared, leave the natural log alone, plus leave the first one alone, take the derivative of the natural log, 1 over x. So ultimately what we have here then is 2x natural log of x plus x. So here is the second derivative, and now we're wondering, is this second derivative positive or negative from 1 to 3? Well, let's look. 2x is clearly positive from 1 to 3. X is also clearly positive from 1 to 3. What about the natural log of x? Well, the graph of the natural logs looks like this. It looks like all the log functions, and this is the point 1 comma 0. So the natural log is also positive from 1 to 3. In fact, from 1 on, the natural log is positive. So therefore, I've got a positive number times a positive number plus a positive number. We are all positive, baby, and this thing is clearly concave up. And that's my answer. Okay, here we are in the final part of the problem for problem 2007, number 4 on the AP Calculus BC exam. In the first two parts, we've been reasoning about this function f of x, which we don't know, but we know some things about it, like its derivative, its value at a certain place, the fact that it's defined when x is bigger than 0. Finally, in the last part, we're going to figure out what this function actually is. And we're going to do that by solving this essentially simple, easy differential equation. We've got dy dx equals x squared natural log. So, in other words, f of x is going to end up being the antiderivative of x squared natural log of x plus this initial value condition that we're giving here. So this is essentially, we're solving an initial value problem. So let's just start by finding the indefinite integral of the natural log of x squared times the natural log of x. So this seems like a pretty hard integral to do, in fact. I tell my students to run through this whole process. Do I know of a function whose derivative is this off the top of my head? The answer usually to that, sadly, is no. Is there, and it's no here as well, is there some algebra that I could do to this that could turn it into an integral that I could do? Like, could I use rules of logs, or if this had trig stuff, is there a trig identity? Or could I, do some basic algebra? I think the answer here is pretty clearly no. I mean, there's some rules of logs we could employ, but that's only going to make this function this integral seem even harder. The next step is there a u substitution that I could make? Well, u substitutions usually take place where there's one function being plugged into another, and I let u be that inside function. The u substitution is kind of an anti-chain rule. I don't have one function being plugged into another here, so I don't think that a u substitution is going to work. After that, the next thing that my students learn is integration by parts, and I wonder if integration by parts could work here. I suspect that that's likely what we're going to do. So that's what I'm going to go with. I'm not sure that this is correct, but that's what I'm doing. So integration by parts. I'm going to let u equal something, and I'm going to let dv equal something. As a general rule, I let dv be the largest thing I can make it be that I still can relatively easily compute the antiderivative of, because that's what I have to do. That means that I'm not going to let dv equal the natural log, because while I can compute the integral of natural log if I try very hard, it's not something that I know relatively quickly. In fact, to compute the antiderivative of natural log by itself requires a whole other integration by parts. So I'm not going to do an integration by parts within an integration by parts. That seems crazy. So I'm probably going to let dv equal x squared dx, and I'm going to let u equal natural log of x. Because now I can do both of these things. So du very nicely becomes 1 over x, and v becomes the antiderivative of x squared, which is 1/3 x cubed. There should be a dx here. And now I'm ready to write what integration by parts tells me this is. So this is u times v, so I have 1/3 x cubed natural log of x minus the integral of v du. So these two things are getting multiplied together. So I see that I have a 1/3 that's going to come out front, and then I have an x cubed times a 1 over x, that's just x squared dx. And so we're almost done with the problem. This ends up equaling 1/3 x cubed times the natural log of x. And then I want to do this antiderivative, but that's just another anti-power rule. So this time I think we're going to have minus 1/9 x cubed plus c. Okay, cool. Now I just need to figure out what the plus c is, but fortunately I know that the function goes through the point e comma 2. So I can use that to figure out what this is. So I know if I called this f of x, which is what it's ultimately going to be. It's not currently f of x because of the plus c. But what it's ultimately going to be, I can figure out what c is by plugging in f of e equals 2. So f of e, which would end up being 1/3 e cubed times the natural log of e minus 1/9 e cubed plus c. Apparently this should equal 2. Now the natural log of e is just 1, so this goes away. And now I have 1/3 e cubed minus 1/9 e cubed, which I believe is 2/9 e cubed. So I think we just found out that c equals 2 minus 2/9 e cubed. And so I plug that back up, and my final answer for f of x is therefore 1/3 x cubed natural log of x minus 1/9 x cubed plus 2 minus 2/9 e cubed. And that's my final answer.